If you haven't yet, take a minute here to pause the video and read that first introductory paragraph at the beginning of chapter 2 in your textbook. So some important ideas from that. This chapter is about the topic of limits, and limits is what separates the math that you've done before from the math that we're going to do in calculus. We said calculus is it's the study of infinitesimals. So we can't understand what infinitesimals are, what it means for something to be infinitely small, until we understand this idea of limits. So this is where we're going to start. We'll find out, I'll summarize here. We can investigate limits using substitution, using algebra, using graphs, using tables. And some of these we've already practiced. We'll see how they come back. Just to clarify a key idea, limits are output values of a function. So you would investigate the limit at a certain input value, but the actual limit is the output value that you would expect. So one way to think about it, limits are outputs. Limits are like y values. They're not like x values. They're not like inputs. They're members of the range, not of the domain of a function. And some big ideas, I said we're talking about limits so that we can understand what infinitesimals are, because that's what all of the rest of calculus is built on, and so that we can more immediately talk about continuity, which is coming up in section 2.3. So a quick reminder of what we did yesterday in class. Average speed can be computed by taking change in distance dividing by change in time. Now, maybe you've already made this connection. We talked a little bit in the first couple of weeks about computing the slope of a function, even a function that's not linear. So you can see that operation, that process, change in y over change in x, change in output over change in input, that's the same idea. It's the same calculation to find slope, to find average speed. And then that next question do we remember how to compute instantaneous speed? Well, instantaneous speed, this is where we get into the mathematics of change. We want to talk about how to compute use that same process, change in distance over change in time, but let the change in time shrink towards 0. And that was our first look at a limit, but we didn't use any limit notation. So that's what we want to introduce today. Here is the exact same math that you saw yesterday. If I wanted to compute the instantaneous speed of a rock falling with a position function of 16y squared, if I want the instantaneous speed at exactly 2 seconds, I'm going to use two time values, time 2 and time 2 plus a teeny tiny bit, and I gave that tiny bit a name. I called it h. So same process here. What I want to do here on this next slide is notice that same math, that process, it describes a new notation that we're going to use, this idea of a limit. So check this out. Same math. All I'm going to change is sort of this subscript on this side. So the instantaneous velocity, I see here that my slide is missing 2 subtraction signs, so I'm just going to fill them in. That should be minus, there should be a subtraction sign here. Okay, so the instantaneous velocity is the limit as h approaches 0 of the position at time 2 plus h minus the position at time 2 all over, where did that h come from? That was 2 plus h minus 2. So we talked about how to do this using smaller and smaller values of h plugged in. We talked about a way to simplify this with algebra, and then we could plug in 0 for h at the end. But those are two different ways to think about this same idea. If I could let h get smaller and smaller and smaller, so small that h was 0, I'm going to have the instantaneous speed. So what I read here, and you can see I've written it at the side, if I was going to say sort of that last line at the end using limit notation, limit language, the instantaneous velocity is equal to the limit as h approaches 0 of 64 plus 16h. So the velocity is 64 plus 16h with the idea that h is going to get closer and closer and closer and closer to 0. So one way to think about what we just did, we found the limit as the change in time approached 0 of the slope of that position function the 16y squared position function. So let's take a look at another function. We're going to talk about the limit. So we said that we can investigate limits with graphs. and with tables. So we're going to do that here with this example. This is a graph of y equals the sine of x all divided by x. Here's a graph for you. So what happens to the y value as x gets closer and closer to 0? We know we can't simply replace x with 0 to find that answer, because I'll end up with a sine of x, sine of 0, divided by 0, and division by 0, as much as we wish we could do it, it's still undefined. So if we use the graph, however, it seems kind of obvious what the limit's going to be. Let's use a different color here. If you could imagine walking along this graph, and you were wondering, hey, when I get to the place where x equals 1, what do I think the y value is going to be there? Kind of looks like it's going to be the y value of that point I just circled. If I approached from the other direction, same thing happens, right? It looks like I'm going to end up at that same place where the y value is 0. This is one way to investigate. We could use a table of values too. Your calculator is set up to do that. You could graph that function, sine of x divided by x, and then use the table feature to check in. And you can see as we look at values of x that are getting closer to 0, but are to the left of 0, so a little bit negative, we can see these values get closer and closer and closer to 1. You can see there isn't much of the table on the other side of x, but you can see that the values, if you scroll down and can see the rest of the table, get closer and closer and closer to 1 as x approaches 0 from the left. So we draw this conclusion. We looked at the graph, we looked at this table. It looks like the limit of sine x divided by x as x approaches 0 is that output value we were expecting, the output of 1. So the limit is 1. Look here, if you actually plug in 0, you're not going to get a result because because sine of 0 divided by 0, which makes 0 over 0, is undefined. So ladies and gentlemen, here is limit notation. This I would read as, the limit of f of x as x approaches c is L. So in that example we just looked at, the interesting place we were looking at was where x equals 0. I would say that the limit as x approaches 0 of sine x divided by x is 1. Notice how that limit, the output value, that limit 1, it's an output value. It's the y value of the graph at the place, well, it's the y value I was expecting on my graph at the place where x equals 0. Turned out it didn't actually happen, but still, it's still the limit, even though that 1 point isn't filled in. So here's the big idea. The limit of a function refers to what that function approached from both sides, regardless of what actually happens at that one x value. So here's an example. If I walked along this graph, coming toward the place where x equals 2, it looked like my y value was supposed to be 2. If I came from this direction, same thing. It looked like the y value I was expecting to step into was 2. The limit as x approaches 2 of f of x is this y coordinate 2. In contrast, f of 2, the function value, that's the colored in dot. So f of 2 is 1. But the limit, which is what we're talking about today, is that value that I was approaching, whether it actually happened or not.